Well, I have 7 o'clock, so it must be time to start. Amateur Radio Technician Exam Prep Course, Module 4, Propagation, Antennas, and Feed Lines. Propagation. Radio waves propagate in many ways, depending on the frequency of the wave and the characteristics of the environment. We will discuss 3 basic ways that they propagate: line of sight, ground wave, and sky wave. Line of sight. This is generally what you have on 2 meters and higher in frequency or lower in wavelength. Radio energy can travel in a straight line from a transmitting antenna to a receiving antenna called the direct path. There is some attenuation of the signal as the radio wave travels due to the fact that they spread out. This is the primary propagation mode for VHF and UHF signals. Radio waves can be reflected by any sudden change in the path they are traveling, such as a building or even weather-related hill or even weather-related changes in the atmosphere. Vegetation can also absorb VHF and UHF radio waves. Precipitation, such as fog and rain, can absorb microwave and UHF radio waves, although it has little effect at HF and on the lower VHF bands. Ground wave. At lower HF frequencies, radio waves can follow the Earth's surface. These waves will travel beyond the range of line of sight, range of a few hundred miles. For instance, everyone has listened to distance AM radio stations. When I was younger, that's where where I was in college, that's where you could hear music, was from stations out of Indiana and Tennessee and things like that. Reflect, refract, and diffract. Radio waves are reflected by any conductive surface: ground, water, or buildings. Refraction or bending occurs when waves encounter a medium having a different speed of light, such as water or an electrical feed line. By bending signals slightly back toward the ground, refraction counteracts the curvature of the Earth and allows signals to be received at distances beyond the visual horizon. Knife edge diffraction. Diffraction is waves travel past sharp edges or large objects. Multipath. Radio signals arriving at a receiver after taking different paths from transmitter. For instance, the reflections we were just talking about off of a building results in irregular fading even when reception is generally good. Those different paths can occur in the ionosphere. Because dead spots from multipath are usually spaced about a half wavelength apart, VHF or UHF signals from a station in motion can take a rapid variation in strength known as mobile flutter or picket fencing. The distortion caused by multipath can also cause VHF and UHF digital data signals to be received with a higher error rate, even though the signal may be strong. Tropospheric propagation. Propagation above VHF frequencies are assisted by variations in the atmosphere. Variations such as weather fronts or temperature inversions create layers of air next to each other that have different characteristics. The layers form structures called ducts that can guide even microwave signals for long distances. This happens quite often over the ocean. Regularly used by amateurs to make VHF and UHF contacts that would otherwise be impossible by line of sight propagation 300 miles or more. Our practice questions. Why do VHF signal strength sometimes vary greatly when the antenna is moved only a few feet? And that would be multipath propagation cancels or reinforces signals. So quite often you'll hear somebody on 2 meters say, move over or mark that spot, because right where you were at the time was a really good place to get into a repeater or into the person you were talking to. What is the effect of vegetation on UHF and microwave signals?
Howard,
Yes.
before you continue, may I say something about moving antennas?
Certainly.
Okay. Now this has to do with VHF and UHF. I had set up a new antenna and I wasn't pleased with it because I felt like it could be and should be more efficient. And I wasn't getting into a couple of repeaters that I thought I should be getting into. I went out back and moved that antenna 4 feet. That's all I moved it, just 4 feet. And the efficiency of that antenna improved over 50%. I was getting into more repeaters, better signal strength to the ones I'd already been getting into, and it helped tremendously. So in that case, I found what you would call the sweet spot, but I only moved it 4 feet. So, you can do that if you think you put up one and it's not working like it should. Move it a little bit and try it again and see what happens. Thank you, Howard.
You're welcome. What is the effect of vegetation on UHF and microwave signals is absorption. What is the meaning of the term picket fencing? That is B, rapid flutter on mobile signals due to multipath propagation. What weather conditions might decrease range at microwave frequencies? That, I believe, is C, precipitation. What is likely cause of irregular fading of signals propagated by the ionosphere? And that is random combining of signals arriving by way of different paths. What effect does multipath propagation have on data transmissions? And that is error rates are likely to increase. What is the effect of fog and rain on signals in the 10-meter and 6-meter bands? And on those, there's little effect. Which of the following effects may allow radio signals to travel beyond obstructions between the transmitting and receiving stations? Let's see. I believe that would be your knife edge diffraction.
Howard?
Yes.
That's what I believe lets me get into the Caesar's head repeater.
I can understand. You got a ridge up there.
It's called the Blue Ridge Parkway, and it's 5,600 feet tall. My house is at 2,200 feet, and the Caesar's head repeater is at 3,500 feet. And just looking at, are there notches in the mountain and places like that? Are there things I could bounce off of? No. So my conclusion is that as my signal goes over the edge of that mountain, it's doing that spreading out, and I'm getting down into that repeater. That's the only explanation I found that explains why I can get into that repeater with 5 watts. Now I've got a big object between me and the club repeater that takes 20 watts to get through, and it's only 6 miles away.
Yeah.
Anyway, back to you.
The following, well, that was knife edge diffraction. What type of propagation is responsible for allowing over the horizon VHF and UHF communication ranges of approximately 300 miles on a regular basis? I believe that is tropospheric ducting, and quite often a temperature layer over the ocean will cause the duct between the ocean and that temperature layer. I've heard of a lot of people working from Hawaii into California on VHF if they're at the right altitude. What causes tropospheric ducting? That would be D, temperature inversions in the atmosphere. Why is the radio horizon for VHF and UHF signals more distant than the visual horizon? The atmosphere refracts radio waves slightly. The ionosphere, ionized gases from 30 to 260 miles above the surface of the Earth. Atmosphere thin enough for atoms to be ionized by solar ultraviolet radiation. Ions are electrically conductive. Because of varying density, the ionosphere forms layers with different amounts of ionization. Ionization varies with solar illumination, hourly, and intensity of solar radiation. One of the things that changes solar radiation intensity is sunspots. Higher ionization refracts or bends radio waves more strongly. The ionospheric layers. Layers D, E, F1, and F2. Depending on whether it is night or day and on the intensity of solar radiation, these layers can refract the E, F1, and F2 layers, or absorb D and E layers. Excuse me. Of radio waves. Each reflection from the ionosphere is called a hop, and they can go hundreds or thousands of miles. Sunspot cycle activity. We are just past the sunspot cycle peak in this part of the cycle. The level of ionization depends on the intensity of radiation from the sun. Radiation from the sun varies with the number of sunspots on the sun's surface. Higher numbers of sunspots results in higher level of ionizing radiation emitted from the sun. Sunspot activity follows an 11-year cycle. F layers can reflect 6 meter, 50 megahertz signals at the sunspot cycle's peak. That's why they call 6 meters a magic band. Patches of the E layer can become sufficiently ionized to reflect VHF and UHF signals This is called sporadic E, most common during early summer and midwinter months on 10 and 6 and occasionally 2 meters. The ionosphere and RF mirror. Ionosphere can refract radio waves back to the Earth. It acts like a reflection. Most refraction occurs in the F layers. Reflection depends on frequency and angle of incidence. Too high a frequency or angle, and the waves are lost to space. They go right through. Ionosphere continued. The highest frequency signals that can be reflected back to a point on the Earth between the transmitter and the receiver is the maximum usable frequency. Skywave or skip propagation is responsible for most over-the-horizon propagation and HF and low VHF 10 and 6 meters during peaks of the sunspot cycle. Skip is very rare on the 144 megahertz and higher UHF bands. I think when contesting, we were over near Chattanooga and had the best 144 megahertz skip was from just above Chattanooga, Tennessee, on a pull off on the interstate there, 75, into Texas. E region of the ionosphere is also home to meteor trails. Bouncing signals off of these ionized trails is called meteor scatter propagation. The best bands for meteor scatter is 6 meters, and contacts can be made at distance up to 12 and 1,500 miles. This is a type of work where you transmit a very high-speed signal, and it may be a good bit of time between two meteors before you can complete a communication between two stations. And then at other times you get a bigger meteor that burns up that can last longer. Practice questions. Which region of the atmosphere can refract or bend HF and VHF radio waves? And that would be A, the stratosphere. Why are simplex UHF signals rarely heard beyond their horizon? And that would be UHF signals are usually not propagated by the ionosphere. It takes an extremely dense ionosphere to raise frequencies. What is a characteristic of HF communication compared with communications at VHF and higher frequencies? And that would be long distance ionospheric propagation is far more common on HF. That's why it's more fun. What is a characteristic of VHF signals received by an auroral backscatter? They are distorted and signal strength varies considerably. Which of the following types of propagation is most commonly associated with occasional strong signals on the 10, 6, 2 meter bands from beyond the radio horizon? And that would be sporadic E. I believe those clouds can move around during times of the day. What band is best suited for communication via meteor scatter? 6 meters, 50 megahertz. What is generally the best time for long distance 10 meter band propagation via the F region? From dawn to shortly after sunset during periods of high sunspot activity. After sunset, the ionosphere stops getting the solar radiation and becomes less dense. Which of the following bands may provide long-distance communication via ionosphere's F region during the peak of the sunspot cycle? That would be A, 6 and 10 meters. Antenna and radio wave basics. The antenna system. Antenna transforms current into radio waves to transmit, and vice versa, converts radio waves into current. Feed line connects your station to the antenna. Test and matching equipment allows you to monitor and optimize the antenna system performance. For an antenna to do that job efficiently, its dimensions must be an appreciable factor of the signal's wavelength. The radio wave is an electromagnetic wave that contains both electric and magnetic energy or fields created by the RF current. The RF current in your antenna creates an electromagnetic wave. That wave builds and drops. As the wave diminishes, it generates the electric wave. And when it diminishes, it generates the magnetic wave. And electromagnetic waves go on forever. They get weaker because they get spread out. The electric and magnetic fields are at right angles to each other and oscillate at the same frequency as the RF current in the antenna. Antenna vocabulary. Element, the conducting part or parts of an antenna designed to radiate or receive radio waves. Driven element, the element supplied directly with power from the transmitter. Array, an antenna with more than one element. Parasitic element, elements not connected directly to a feed line. Resonant, an antenna is resonant when the feed point impedance has zero reactance. Feed point, where the transmitted energy enters the antenna. Radiation, not radioactivity, an antenna emitting electromagnetic waves. Let me back up just a second and talk about resonant. An antenna is resonant when its feed point impedance has zero reactance. This happens when it is at a half wavelength or a multiple of a half wavelength. Electromagnetic waves. Radio waves are electromagnetic waves. Electric and magnetic fields at right angles to each other, oscillating at the wave's frequency. Spread out into space from the antenna. Created by AC current. Wave and current have the same frequency. Wave polarization refers to the orientation of the radio wave's electric field, vertical or horizontal, determined by elements, can be circular if the orientation twists as the wave spreads through space. Combinations of polarizations are called elliptical polarization. Both vertical and horizontal antennas are effective for receiving and transmitting on the HF bands where skip propagation is common. When the polarization of transmit and receive antennas aren't aligned the same, the received signal can be dramatically reduced less current is created in the antenna. One thing that they don't say about that is while in VHF, most of our antennas are oriented vertically because those are the frequencies most used in mobile communication where those antennas are vertical. If you're using a horizontally polarized antenna or horizontal antenna, you can have up to 20 dB difference in those two, and 20 dB is 200 times less signal. No, I take that back. It's 100 times less signal. I'm sorry. 20 dB is 100 times less signal. However, when your signal goes through the ionosphere and is diffracted back to Earth, you do not know what that polarization will be when it appears at your antenna, and changes in that may be one of the reasons why your signals will go up and down, as well as multipath. Summary: antenna and wave propagation must match for maximum reception, especially at VHF and higher frequencies. Practice questions. What happens when antennas at opposite ends of a VHF or UHF line of sight radio link are not using the same polarization? And that would be B, received signal strength is reduced. Which of the following results from the fact that signals propagated by the ionosphere are elliptically polarized? Either vertical or horizontally polarized antennas may be used for transmission or reception. What is the relationship between electric and magnetic fields of an electromagnetic wave? And the answer is D. They are at right angles. And they don't mention it, but they're 90 degrees out of phase. The orientation of the electric field. What property of radio wave defines its polarization? The orientation of the electrical field, or orientation of the magnetic field. The orientation of the electrical field. What are two components of a radio wave? Electric and magnetic fields. Antenna. Some vocabulary. Gain. Apparent increase in a particular direction by focusing radiation in that direction, measured in decibels. Isotropic, equal radiation in all directions. Omnidirectional, no preferred horizontal direction. Directional, antenna that focuses radiation in specific directions. These are radiation patterns that show the directions of signal strength from an antenna. And the azimuthal pattern is your horizontal, and the elevation pattern is your vertical. Radiation patterns are a way of visualizing antenna performance. The further the line is from the center of the graph, the stronger the signal at that point. Graphs are calibrated in decibels. Decibels are logarithmic terms mathematically. Most common types of radiation pattern is azimuthal pattern that shows the antenna's gain in horizontal directions around the antenna. An elevation pattern shows the strength of the radiated energy in vertical directions as if the antenna is viewed from the side. Radiation pattern vocabulary. Nulls, directions of minimum gain. Lobes, directions between nulls. Main lobe, lobe with the highest gain. Side lobe, any lobe other than the main lobe. Forward gain, gain in the direction assigned as forward. Azimuth pattern, radiation pattern showing gain in all horizontal directions around the antenna. Elevation pattern, radiation patterns showing gain at all vertical angles from the antenna, often restricted to angles above the horizontal, mainly because we don't radiate under the ground. Front to back ratio, ratio of forward gain to gain in the opposite direction. Front to side ratio, ratio of forward gain to gain at right angles to the forward direction. Decibels, pronounced dB. A ratio expressed as a power of 10 to make large numbers easier to work with. Decibels are measured in the ratio of two quantities as a power of 10. The dB log is a power ratio. dB, decibel, equals 10 times the log of the power ratio, or dB equals 20 times the log of the voltage ratio. Positive values in dB are indicated by ratios greater than 1, and negative values in dB are for ratios less than 1. Antenna gain is discussed in terms of dB. Let me expand just a little bit there. If you have an amplifier on your transmitter, it is also expressed in terms of dB, one power, the power in to the power out. And it is my recommendation, especially VHF, to go for the bigger antenna before you go for the power amplifier, because antenna gain works in both directions, receive and transmit, whereas your amplified power only works in one direction, and if you can't hear him, how do you know you're talking to him? What is antenna gain? A, the additional power that is added to the transmitter power. B, the additional power that is required in the antenna when transmitting on a higher frequency. These are questions, aren't they? What is antenna gain? And that would be C, the increase in signal strength in a specified direction compared to the reference antenna. Which decibel value most closely represents a power increase from 5 watts to 10 watts? That is 3 dB. Which decibel value mostly represents a power decrease from 12 watts to 3 watts? That is minus 6 dB. Which decibel value represents a power increase from 20 watts to 200 watts? That would be A, 10 dB. Now, I know that ran through that rather quickly, but the one thing that you need to remember for the test is 3 dB is equal to doubling the power, or having the power. Power change is 50% in either direction. 10 dB is equal to 10 times the power, or a tenth of the power, depending on whether you're looking at positive or negative. So if you're going to raise something times 4, you would say 3 dB plus 3 dB is 6 dB is equal to doubling the power twice. Every time you double the power, it's 3 dB. Now, if you're used to using logarithms, you can get everything in between all that when you look at the logarithmic number of what you're working with. Feed lines and SWR, which is standing wave ratio. The purpose of the feed line is to get RF power from your station to the antenna. Basic feed line types: coaxial cable and open wire line, sometimes called ladder line or window line. And you can even make it yourself if you have spacers to space your line and work with the impedances. Power lost as heat in the feed line is called loss, and it increases with frequency. Feed lines used at radio frequencies use special materials and construction methods to minimize power being dissipated as heat by feed line loss and to avoid signals leaking in or out. Feed line vocabulary: center conductor is the central wire. Dielectric, insulation surrounding a center conductor. Shield, braid or foil surrounding the dielectric. Jacket, protective outer plastic coating. Forward or reflected power, RF power traveling toward or away from a load such as an antenna. And here is a picture of coaxial cable. And you could see why you would call it a center conductor, being as it's round. And some of the very expensive stuff that they use on high power transmission, like at TV stations, will be a pipe with a air around some kind of a solid conductor that's in the middle of it. So the single shielded has a single braid around your dielectric. A double shielded will quite often have a full wrap around there with a braided shield. Vinyl is usually your jacket. And the first we were looking at is the single shielded, then the double shielded. Then there's rigid hardline. And that's a fairly soft, usually aluminum outer conductor, and has less loss than the single shielded or double shielded. And the semi-flexible hard line is about the same thing as the rigid hard line, but it's made so that it bends easier. Coaxial cable. Most common feed line. Easy to use. Carries radio signals on the surface of the center conductor and the inside of the shield. And it's not affected by nearby materials. Has higher loss than open wire line at most frequencies. Air-insulated hardline has the lowest loss, but limits the amount of bending. Now, this is what open wire line, those of you that are a little older might remember the 300 ohm twin lead is your common antenna connection for your TV. And the 450 ohm window line is what's used quite often in amateur radio equipment, in that you have a much less loss with a long run with those, but you have to be careful not to get it around metal objects. Lighter and less expensive than coax. lower loss than coax at most frequencies. More difficult to use since it is affected by nearby materials. Requires impedance matching equipment to use with most transceivers. Open wire feed lines cannot be buried or installed in metal conduits and must be kept clear of nearby conducting surfaces. Characteristic impedance. The impedance presented to a wave traveling through a feed line. It is given in ohms and its symbol is Z0, zero being an O with a line through it there. Depends on how the feed line is constructed and what materials are used. Coax are usually 50 or 75 ohms, the ones that we use anyway. Open wire line 300, 450, and 600 ohms. Most coaxial cable used in ham radio has a characteristic impedance of 50 ohms. Standing wave ratios. If the antenna feed point and feed line impedances are not identical, some RF power is reflected back toward the transmitter, called a mismatch. Forward and reflected waves create a pattern of standing waves of voltage and current in the line. SWR is the ratio of standing wave maximum to minimum. It's measured with an SWR meter or SWR bridge. Continued. Reflected power is re-reflected at the transmitter and bounces back and forth. Some RF power is lost in heat on each trip back and forth through the feed line. All RF power is eventually lost as heat or transferred to the antenna or load. High SWR means more reflections and more loss of RF power, less transferred to the antenna or load. SWR equals the ratio of feed point or load and feed line impedance, whichever is greater than 1. SWR is always greater than 1. What is an acceptable SWR? 1 to where 1 is SWR is perfect, no power reflected. Up to 2 to 1 SWR is normal. Modern radios lower transmitter output power for protection when SWR is above 2.1. Couple of things I'd like to mention here. They talk about the power reflecting back and forth. All the power that you put into your coax is either turned into heat or radiated by your antenna. The losses are higher when you have the reflected waves because they're traveling two waves, the reflected and the forward wave, back and forth, that increase the resistive loss. But all the power is either radiated by the antenna or turned into heat in the coax. And they said that the matching impedance, and as we said earlier, an antenna is matched when there is when it is at its resonant frequency, and it's resonant at one frequency. As you go up a band, you go away from that frequency. As you go down a band, you go away from that frequency. So you're always usually looking at some SWR unless you're exactly on the frequency the antenna was cut and matched to, if that makes sense. So SWR is something that you minimize, but generally have to live with, unless you pick one frequency and stick to it, like broadcast transmitters. SWR above 3 to 1 is considered high in most cases. Erratic SWR readings may indicate a faulty feed line connections, or a faulty antenna. High SWR can be corrected by tuning or adjusting the antenna with impedance matching equipment at the transmitter called an antenna tuner or transmatch. It doesn't tune anything, it really does the matching. Does not change the SWR in the feed line. That you're going to have to live with unless you're, again, on that one frequency that antenna was made for. Practice questions. What happens to power lost in the feed line? It is converted into heat. What is the most common impedance of coaxial cable used in amateur radio? 50 ohms. Why is coaxial cable the most common feed line for amateur radio antenna systems? It's easy to use and requires few special installation considerations. And also because that's what your transmitter output on modern radios are designed to do. Back in tube days, you matched the impedance of your output devices, which were vacuum tubes, to your transmission feed line with a circuit in the radio. They don't do that anymore. What happens as the frequency of a signal in coaxial cable is increased? That would be D. The loss increases with frequency. Which of the following types of feed line has the lowest loss at VHF and UHF? And that would be C, air insulated hardline. That would also be expensive. Which of the following should be considered when selecting an accessory SWR meter? And the frequency and power level at which the measurements will be made. What reading on an SWR meter indicates a perfect impedance match between the antenna and the feed line? That would be C, 1 to 1. Why do most solid-state transmitters reduce output power as SWR increases beyond certain levels? That would be A, to protect output amplifier transistors. What does an SWR reading of 4 to 1 indicate? And that would be an impedance mismatch, D. What is the benefit of a low standing wave ratio, SWR? And that would be reduced signal loss, B. What can cause erratic changes in SWR? Loose connection in the antenna or feed line. What is standing wave ratio? A measure of how well a load is matched to a transmission line. Practical antenna systems. Dipoles. Simplest type of antenna. Dipole means two electrical parts. Di meaning two. made from a straight conductor or wire 1/2 wavelength long with a feed point somewhere along the antenna. Most are oriented horizontally, particularly on lower frequencies bands, and radiate a horizontally polarized signal. This is because most people on 160 meters don't have what is it? 62-foot vertical, which would be a quarter wavelength, half of the antenna. Most are oriented horizontally, particularly because on lower frequency bands, because you can put something up between two trees. Can also be installed vertically, sloping or even drooping from a single support in the middle. And again, this is the dipole. The radiation pattern, isolated in space, looks like a donut. Ground plane antennas. Most common type is 1/4 wavelength long with a feed point at its base. I just happen to have one in front of me here. Can you see this? That is a ground plane antenna. It has a vertical and 4 horizontals, which is the counterpoise for that vertical. And this one was made for 1.2 gigahertz, 1,296 megacycles, which is why it's that small. To make one, again, at 80 meters, takes a 64-foot or 65-foot vertical with 65-foot radials laid around it. Most common type is 1/4 wavelength with feed point at the base. Acts like 1/2 of a dipole with the missing portion made up by the electrical mirror formed by the ground plane. Made from sheet metal or screen wires called a screen of wires called radials that extend out from the base. Extended length of a 5/8 wave ground plane focuses more energy toward the horizon and giving you better range. This is why you see them quite often for a 2-meter mobile antenna, 5/8 wave being roughly 39 inches long, where your normal quarter wave is about 19. To reduce the physical size of the antenna, it is often constructed with some of the radiating conductor wound into a coil or separate inductor inserted in the antenna is called inductive loading. Figure 10, a ground plane makes up an electrical mirror. In this case, it actually has a conductive plane, which could very easily be the metal roof of your car. This is one like I just held up a minute ago, where it has the vertical and has 4 radios coming from it. And this is common when you put in a lower frequency vertical. Then they'll have as many as you want to put around it, radials, to create that conductive plane. And back over here on the left is the regular dipole with 2 insulators and one in the middle, and this is where you connect your feed line. Antennas for handheld radios. Flexible antennas we use with most handheld radios is called a rubber duck. Ground plane antenna shortened by coiling the conductor inside a plastic coating. Doesn't transmit or receive as well as a full-size ground plane antenna. For best performance, hold the transceiver so that the antenna is vertical. and it's not very effective inside vehicles, up to 20 times less effective than an external mobile antenna. Easy to connect handhelds to full. It's easy to connect handhelds to full-size antenna. Uses standard RF connector. A 5-watt handheld can easily reach 10 miles with a good antenna. One thing that, when I was talking about my ground plane here, the radios that come off of it, the reflected plane, if you have a speaker mic on your handheld and hold the handheld away, the shielding on that mic cable acts as part of your antenna to help the radiation, acting more as that counterpoise or the other half of the antenna. Calculating antenna length in dipoles. To calculate length of a resonant dipole, a half wave long, the length in feet is equal to 468 divided by the frequency in megahertz, or 406 divided by F. And as we talked about back in lesson 2, the other number you can use is 300 million meters per second divided by the frequency in megahertz. That gives you the wavelength in meters, and then you divide that by 2 to get a half wavelength. Example, at 50.1 megahertz in the 6-meter band, dipole length is calculated as 468 divided by 50.1 equals 9.33 feet, or 112 inches. Note, the value of the constant used in the formula accounts for the effects that cause the antenna to act like it is a little longer electrically than physically. The actual resonant length is affected by height above ground, its electrical properties, and nearby conductive objects. So, make the dipole a few percent longer at first. Use 490 instead of 468. Then use an SWR meter or antenna analyzer to determine the resonant frequency. Assuming the requisite resonant frequency is too low because the dipole is too long, shorten it a little bit at a time until the dipole is at the desired frequency. Calculating ground plane length. The length of a ground plane antenna is half that of a dipole and is often estimated as 234 divided by the frequency in megahertz. For example, at 146 megahertz, a quarter wave ground plane is 243 divided by 146 equals 1.6 feet, or 19.25 inches long. Length adjustments also apply. Usually when you buy a quarter wave mobile antenna, it'll have a set screw so you can take that radiating element out and trim a little off of it to adjust it down to your frequency. If you buy something like that, check it. Don't assume that it's right. Directional antennas. Simple dipoles, ground planes, and loops work well, but they have little gain. Radiation patterns don't have strong preferred directions. Use a directional beam antenna, get the best reception in one direction. On VHF and UHF, if a direct signal path is blocked, a beam antenna can be used to aim the signal at a reflecting surface to bypass the obstruction. most widely used type of beam antennas are Yagis. They're sometimes called Yagi Udas, named after the Japanese man that had invented them in the 1920s. Yagi beam antennas have much more gain than omnidirectionals in their preferred direction. The radiation pattern of a typical 3-element Yagi antenna with a driven element, reflector, and director shows that most of the antenna's energy is focused in one direction. Along the boom of the antenna, along the 0 through 180-degree axis of the graph. Smaller amounts are radiated toward the side and back. This antenna also rejects noise and interference from the side and the back. The round pattern of the isotropic antenna and the figure 8 pattern of the dipole are included for reference. An isotropic antenna being a perfect radiator, the one that we are most exposed to is the sun, which radiates in all directions. N7 CFO's dish antenna operates on 10 gigahertz and is portable enough to be taken on contests. Horizontally polarized Yagis are usually used for long-distance communication. Results in lower ground losses when the wave reflects from or travels along the ground. As frequency increases and the size of Yagi elements becomes smaller, it becomes more difficult to construct practical antennas. Above 1.6 above 1 gigahertz or 1,000 megahertz, dish antennas become practical. Practical questions. Which of the following describes a type of antenna loading? A. Electrically lengthening by inserting inductors in radiating elements. Putting a coil in your radiating element. Which of the following describes a simple dipole oriented parallel to the Earth's surface? And that would be A, I believe, or to get A, B, horizontally polarized antenna. I'm sorry, it is a horizontally polarized antenna. Ground wave's what you get from it. What is a disadvantage of the short, flexible antenna supplied with most handheld radio transceivers compared to a full-size quarter-wave antenna? And that one would be A, it has low efficiency. Which of the following increases the resonant frequency of a dipole antenna? That would be C, shortening it. What is a disadvantage of using a handheld VHF transceiver with a flexible antenna inside a vehicle? And that would be A, the signal strength is reduced due to the shielding effect of the vehicle. Your signal does not go through metal. What is the approximate length in inches of a quarter wave vertical antenna for 146 megahertz? That would be C, 19 inches. What is the approximate length in inches of a half wave length 6-meter dipole antenna? I believe that one is 112 inches. Which direction does the half-wave dipole antenna radiate the strongest signal? And that is D, broadside to the antenna. What is an advantage of a 5/8 wavelength whip antenna for VHF or UHF mobile service? It has, well, let's see. It has more gain than a quarter wavelength antenna by reducing the angle of elevation of radiation. What antenna polarization is normally used for long distance CW and sideband contacts on the VHF, UHF bands? And that would be C, horizontal. When using a directional antenna, how might your station be able to communicate with a distance repeater if buildings or obstructions are blocking it in the direct line of sight path? That would be B. Try to find a path that reflects signals to the repeater. That can be especially true here in the mountains. What is a beam antenna? An antenna C, an antenna that concentrates signals in one direction. Another thing that you're quite familiar with usually, being as light is also an electromagnetic radiation, is the beam headlight of a car that concentrates all its radiation in one direction. So an antenna that concentrates signals in one direction. Which of the following types of antenna offers the greatest gain? That would be D, the Yagi. Practical feed lines and associated equipment. Table 4.1. Common types of coaxial cable. RG6 is 75 ohm. Its loss per 100 foot is 1.4 decibels. At 30 megahertz, not decibels, 1.4 at 30 megahertz, and per 100 feet at 150 megahertz is 33. This is most typically seen as a television antenna coax at 75 ohms. RG8, loss per 100 foot at 30 megahertz is 1.1, and loss per 100 at 150 is 2.5. RG8X is a little worse at 2 to 4.5. RG58, 2.5, 5 and 5.6. RG59 is another 75 ohm coax. Again, this is quite in use when you were using a vacuum tube type transmitter. RG174, that's a little bigger than 1/8 of an inch in diameter, and it has 4.6 and 10.3 and loss. RG213 is maybe a little smaller than RG174, but it's also a Teflon type insulated, and it's good at 1.1 on 30 megahertz and 2.5 at 150 megahertz. LMR 400, again 50 ohms. It's very good at 0.7 and 1.5. However, we have learned that LMR 400 has some problems if you try to use it with a repeater, but in a home radio system where you're not transmitting and receiving at the same time, it doesn't give you the problems. and it's pretty good coax. Performance of coaxial cable depends on the integrity of its outer jacket. Moisture contamination is the most common cause of coaxial failure. Prolonged exposure to ultraviolet energy and sunlight will also cause the plastic in the jacket to degrade, then cracks, then moisture. Some coaxial jackets use a pigment to absorb and block UV. Coax should not be bent sharply, can shorten the center conductor to outer braid distance and cause a impedance mismatch. This is showing you a bunch of different types of antenna connectors. I would say that the UHF is the most common we use. We call it a PL 259. It looks like that. SMA is what's used on most of your handheld radios. They have used the B and C in the past on handheld radios. N connectors, that's used at higher frequencies like 450 and above. It's quite all common, or maybe down to 450 is our 420 to 450 megahertz ham band. And they refer it as 450 because it is, a round number. And a UHF connector is not necessarily the best for UHF signals. That's just because they were named at a much earlier time. Type of connector used depends on signal frequency. UHF series connectors PL259 and SO239 receptacles are the most widely used for HF equipment. Above 400 megahertz, type N connectors are used. Water in coaxial cable degrades the effectiveness of the braid, the shield, increases losses. In low loss, air core, or open cell phone coax, special techniques are required to prevent water absorption. UHF in this case is not ultra high frequency. SWR meters and watt meters. SWR meters measure standing wave ratio by placing them in series with the feed line, usually right at the output of the radio. Many radios include a built-in SWR meter. Alternatively, a directional watt meter can be used to measure SWR. Measures power flowing toward the antenna and power reflected from the antenna by rotating a sensing element or turning a switch. Antenna tuners. Impedance matches or transmatches or antenna tuners are used if the SWR at the end of the feed line is too high for the radio to operate properly. Connected at the output of the transmitter, adjusted until the SWR measures at the transmitter output is acceptably close to 1:1. Antenna system's impedance has been matched to that of the transmitting output. Most tuners combine the functions of an impedance matcher, directional watt meter, and an antenna switch. Automatic tuners sense when SWR is high and make the necessary adjustments. Antenna analyzers. The popular MFJ series of antenna analyzers are used to adjust and troubleshoot antenna systems. The instrument contains a low power Signal source with an adjustable frequency and an SWR meter. The LCD display shows the operating frequency and information about the antenna's impedance. The meters show SWR and feed point impedance. While popular, new of these are no longer available to my knowledge because Mr. Martin F. Jew has retired and the business is no longer operating. Practical questions. Which of the following causes failure in coaxial cables? That would be A, moisture contamination. Why should the outer jacket of coaxial cable be resistant to ultraviolet light? Ultraviolet light can damage the jacket and allow water to enter the cable. What is a disadvantage of air core coaxial cable when compared to foam or solid dielectric types? And it requires special technique to prevent moisture in the cable. Usually they are pressurized with something like nitrogen. Which of the following types of solder should not be used for radio and electronic applications? Acid core solder should not be used. What is the characteristic appearance of a cold tin lead solder joint? It is a rough or lumpy surface. C. Which of the following RF connector types is most suitable for frequencies above 400 megahertz? Type N or B. Which of the following is true of PL259 type coax connectors? And that would be C. They are commonly used at HF and VHF frequencies. Which of the following is a source of loss in coaxial feed line? A. Water intrusion into coaxial connectors. High SWR and multiple connectors in the line. All of these choices are correct. D. They all cause problems. What is the electrical difference between RG58 and RG213 coaxial cable? RG13 cable has less loss at a given frequency. In the feed line between the transmitter and sorry. Where should the RF power meter be installed? In the feed line between the transmitter and the antenna. Which of the following is used to determine if an antenna is resonant at the desired operating frequency? And that would be B, an antenna analyzer. Which instrument can be used to determine SWR? And that would be D, a directional watt meter. What is the major function of an antenna tuner or antenna coupler? And that would be A, it matches the antenna system impedance to the transceiver's output impedance. And the antenna system is the coax and antenna. We are at the end of Module 4, and we are at 20 minutes after. Do I have questions? And surely there's some questions.
That one, that one part that said, in this instance, the UHF isn't ultra high frequency, then what is it?
It is just the name of the connector.
Oh, okay.
Like I say, when these connectors were designed, probably in the 30s, it might have been earlier, they might have thought of UHF as being a lower frequency than we consider it now. I'm not sure about that, but that is just the name of the connector.
I got you. That makes sense. Thank you.
No
Howard,
problem.
if you look at a lot of the stuff that came out of World War II, which is where coax was started being used,
Yeah,
most of those radio frequencies were in the 6 meter,
yeah,
and that was considered high frequency or ultra high frequency
yeah,
in that day.
yes.
And
Until that time, amateurs generally used probably the 600 ohm wire transmission line because they could make it themselves. It's just a spacer that spaces a consistent spacing between two wire lines, and it still has less loss than coax, but it is a commonly used.
that's some homemade ladder line.
Yeah, you just got to be careful.
Yeah,
Don't run it next to your metal gutters or things like that. It just if you can space it properly to where it doesn't interact. All antennas interact with everything that's around them.
I've got a few here, Howard, if you want me to show them.
Sure, go ahead and show a few, Randy.
Okay. Well, this one is on the HT. This is a Superflex. Did not come with a radio. This is an aftermarket antenna. And the reason why I like this and I keep this on all my HTs, number one, it gives about a half a dB of gain better. And you can see it's Superflex, and walking through the woods, you get it caught on trees, it just flips off. And compared to the rubber duck that comes with this, if you're not careful, the rubber duck, get it caught, it'll break down here where it screws in. Secondly, here's a mobile dual band mag mount antenna. Now this one can only take up to 60 watts, and see it's a magnet. And I prefer mag mount antennas on the vehicles because you can take them off, especially when you go into a enclosed garage
or a car wash.
Yep.
yeah.
Now this one is another dual band mobile. This one is quite a bit longer. This one will take up to 250 watts. Again, as you can see, it's a bigger mag mount. And this is the coax that comes with it, with the PL259. And since we were talking about dipoles, I was showing this earlier. This is a new antenna I just bought to replace my other one. This is a G5RV. This is for HF only. Okay. This is 102 feet long. Right here's where the coax goes in to the connector. It also has 35 feet of ladder line. And it's a center fed dipole. And right there's a center feed. And this one you can put up in several configurations. Horizontal, you can actually use it vertical, but horizontal, you can put it sloped, inverted V, L, or circle, so that you can put it, several different configurations. And what I normally do with my dipoles like this, I run them from north to south. I can still get into Canada and north and south, but it primarily for east and west, as Howard said a while ago. But those are some of the antennas that I have, and my one went bad, so I got to replace it. So I've got to do that. But G5, like I say, is for HF only. The other antennas are dual band, 2 meter and 70 centimeter.
And
Okay.
I have a couple here. This wound on a winder is one that I use if I'm doing summits on the air. And it is a 40-meter dipole. And there are connectors in here that are spade connectors like you see on the end of the wires in cars and stuff. So I can unplug part of it and use it as a 20-meter dipole, but all made into one unit. The white looking stuff on there is the cord that's used to tie it up with, and the black is the wire. And this particular one, yeah, I've got a BNC connector on the thing there. Mainly because the coax that I use, if you're going to walk to the top of a mountain to operate, you carry the lightest equipment you want to be able to use. I have my favorite top of the mountain antenna. This, when it's wound up like this, is a ground plane for 20 meters. It's a fishing rod that you can extend out to 16 feet long that has a wire running down the middle of it, and then 4 sets of radials to lay out around the thing when you're operating it, and a fiberglass stick to stick in the ground to make the thing stand up. My newest, go to the top of the mountain radio is right here. And this is a kind of everything with it. Let's see if I can get that focused. Yeah, there you go. This is the radio. It uses a whip antenna that just happens to have a mount on the side for it that you screw on like that. It's a 5-foot long whip antenna. And this is a 40 through 15 CW transceiver. This is the paddle here for sending the Morse code. And it's a 5-foot whip. And yes, I have made multiple activations with a 5-foot whip from top of a mountain where the entire radio can just about fit in your pocket. But I've been playing with radios a long time. And I still say probably the cheapest antenna you can gain that you can add to your signals is antenna gain. And before you start adding amplifiers, you should put in better antennas.
I'll give you an example, Howard. Before we raised the antenna on our repeater, I was having trouble getting into it from my house, and I think 3.8 miles away. It's just that I have this big chunk of granite between me and the repeater antenna. And I put up a 3-element Yagi, which has got a 6 dB gain on 2 meters. And that antenna was $100. I could not have, let's see, 6 dB is what, 4 times?
4 times the power.
I could not have bought a 4 times amplifier to take 5 watts for $100.
Plus, the antenna works both ways.
Yep, it does. It does. Again, to buy an amplifier would have cost me what those Italian 2-meter amplifiers in the $300 to $400 range for their least expensive ones. And I would have had to have had some extra power and things like that. Whereas when I put this antenna up, I bought a bunch of RG213 out of an estate sale several years ago. So that's what I put that antenna up with, and that was it. So I probably got less than $200 in that total installation because I sacrificed my tree trimming tool, the fiberglass pole in it, to get a 10-foot fiberglass pole up above the chimney.
Yeah.
So that, again, put your money in your antenna, and then you can start thinking about an amplifier. And at HF, you probably need to have a 220 circuit in your shack, which for me to put a 220 circuit from my breaker panel down to where my radio is located, I would have to run about 60 feet of wire out in the yard underground. That's not going to be cheap.
I
can put up antennas cheaper.
I use that 40-meter dipole that I showed you a few minutes ago in 2013, running with 5 watts in one North Carolina QSO party's QRP expedition with over 200 QSOs only on 40 meters between Washington State and Germany.
Yeah.
And I think I did that in 8 hours. Because we quit 2 hours before the VHF contest. I mean, the QSO party was over.
Yeah.
There's so many things that you can get into in amateur radio. Contesting, if you're interested into it. There was this big CW contest this last weekend worldwide. I was chasing new countries on 80-meter CW. But that's the kind of thing. If you get into the thing like summits on the air where you do mountaintops, that's a big thing in Arizona, Charlie. Go to the mountaintop and operate. I have a friend that lives here and there, has 2 houses, and he's a big soda guy that operates from out there.
Yeah, I worked his wife the last time he was here.
Yeah. His wife is about last year got her call.
Yeah.
And it's a lot of fun. The other one is if you do soda, you can't do it near a vehicle. And you can't use anything attached to a vehicle, anything like that. You have to be kind of standalone. And the most recent one that seems to be very popular is called Parks on the Air, where you go to a park and you set up and activate. And they all work to where you get points for activations and stuff like that. And all it gives you is bragging rights until somebody else gets to get more points. But that's kind of the way it runs. You might be one of the people want to reflect that signal off the moon or off that meteor scatter path, or try some of the auroral propagation where you try to use the auroras as your reflecting device up there. It's new antennas. Maybe I want to build one for 10 gigahertz that's a dish. And you see things like that all the time. Now, the one thing, if you're going to do the Earth, Moon, Earth, you need a lot of antenna gain.
Yeah.
I think over 200 dB of antenna gain. When you talk about each direction. but not, I mean, total.
Yeah.
So over 100 dB of antenna gain, and then you might be needing to run a kilowatt to do that. But one of the first ones I saw, man, I think had 64 10 element 2-meter beams. I mean, yeah, 2-meter beams in an array up there that he could tilt, and had the frame of a pickup truck with an electric motor hooked to the rear end to rotate the system. I mean,
Yeah.
and you know, you can go to any extreme that you want in it, or you can just stay home and operate QRP and put up simple antennas and just have fun. You can do everything from cheap to expensive.
Yep.
One of my best friends growing up made his first contact with a $5 one vacuum tube crystal controlled transmitter and a 1938 Silvertone receiver. The 1938 Silvertone, you know, that set upright in the, you know, about
Yeah.
4 foot high.
That was your entertainment center then.
Yeah, so did you see the cartoon the other day with the guy was talking about you didn't have much to do and they finally got a radio and they sat around it? Then eventually they got some power and could listen to it.
Yeah. Yeah, I saw that.
In the museum, we talk about the farm radios, and the farm radios for broadcast back then. They did a lot of education stuff for farmers over the radio in the 20s. And the biggest thing in a vacuum tube radio like that are the filaments, and they were made so that the guy could get the battery out of his tractor and park it where he could roll it off tomorrow and use that battery to supply the filaments. And then they had A and B batteries and stuff like that that were used for the high voltage and different things in the radio. But it's interesting, the development of radio. It all started with a mathematician.
Yep. If you go
Hey,
back,
Howard,
Yes.
I'll say a few things about selecting coax.
Go ahead, Rick.
All right. Generally speaking, larger the diameter of the coax, the less loss it will have at any given frequency. It's a good rule of thumb. And the coax also, it's length dependent on what your total loss is going to be. When you look at the specs, it'll say it loses at this frequency 2 dB per 100 feet. So it's telling you that you're losing, X amount for a 100-foot run. If you only have a 50-foot run, you're going to lose half that amount. So length is a consideration as to how big a coax you need. If you have a VHF/UHF mobile radio in your car and you've got 10 feet of coax going up to your magnetic mount antenna, RG58 is fine. It'll work fine up there at UHF in that short distance. Your losses will be minimum. They'll be there, but they'll be minimum. But if you have 200 feet of RG58, which is 1/4 inch diameter, and you run 200 feet of it out to an antenna, you're going to have so much loss in the coax that you're almost better off putting a rubber duck on a handheld than running that much RG58 coax out to a better antenna, because the antenna will give you some gain, there's no doubt, but how much did you lose in the coax? You have to look at the overall gains and losses. How much am I gaining in my gaining in my antenna? How much am I losing in my coax to get out to that antenna, and so on. It's not hard to do. You just add up the losses in the coax, so many dB, and the gain on your antenna, so many dB, and you can figure out if you're overall ahead or losing.
Like, like Rick said, if you're running it at 2 meters on RG58, it says 5.6 dB. So if you're running 10 feet, it'd be 0.56 dB.
Yeah, because that's 1/10 of 100 feet. So you're only losing half. You're only losing half a dB. That's negligible. Remember, 3 dB means you've lost 50% of your power on coax. If you have a antenna with 3 dB of gain, that means that it's doubling the effective power. But you got to remember, when it comes to gain in an antenna, it's effective power in a given direction, basically where you're pointing that antenna. And the more gain a given antenna has, the narrower that effective direction is. And like somebody else mentioned earlier, that can be a real advantage because you can point the antenna to someone you want to talk to, and the side lobes in the back, it is such a poor receiver on the backside and the sides that it cuts out or reduces, I should say, not it doesn't eliminate it, but it does reduce the noise coming in from those directions, and it focuses on what you want to hear. So better antennas, the more gain you get, the more directional they are, which can be an up and a downside.
And if you have the room and can put up a rhombic antenna for HF, you can make it out of just wire and get 20 dB of gain, but it's got to be 1,200 foot long, and you can't turn it.
Yeah, there is a price to be paid somewhere. I ran what Rick was saying. I had RG8X going up to my 2 meter antenna for probably 10 years. RG8X in a 100-foot run, you're going to lose half of your power. However, when I throw 50 watts out of the radio and 25 makes it to the antenna, it's going to get that 3 miles to the repeater antenna with no problem. When I went in and when I got that RG213, it only loses, it's either 25 or 30% in 100 feet, and I'm only running about a 40-foot run of coax to start with, but I was able to cut the power on the radio back and still get into the repeater. And that, I'd say that cost me that $100 for the antenna, which an amplifier would have done the same thing with the old stuff, but it'd been a whole lot more expensive. And it would be something I'd have to keep up with. And when I put that antenna up, I did all the weatherproofing and stuff like that, stuff that you do for something that you're going to leave up there for 20 years. Hopefully. Unless Helene comes along and moves something down.
Come on, got to be another question somewhere. The RG6 is a really inexpensive coax. It can't handle any power to speak of, is what the problem with it is. However, if you have a receive antenna that's a receive only antenna, it is a good feed line for it. And they make directional antennas invented by Mr. Beveridge, and it's called a Beveridge antenna, and it can be laying on the ground, and there's a company that uses that RG6 as the feed element for that antenna. The longer it is, the more directive it is, but it is a receive only antenna.
The other comment I'd make on coax is when you're looking at spending money, that is not the place to save money. I've got a piece of RG316 here, which is not a good coax for UHF, VHF because the losses are real high. However, if you're only going to run 6 inches of it inside your radio, who cares? But I built an antenna out of that and worked quite well. And one night I turned the radio on and I don't know what went wrong, but the tuner went crazy. SWR went out the roof, and I went out the next day and took the antenna down to check my connections. And as I was running my hand down that one section of the antenna made out of the RG316, I discovered that I had evaporated not only the jacket, but the braid on that RG316. Now that was some Chinese made RG316. Again, if you go, when you're looking at where to spend your money, don't buy cheap coax.